So I'm going to. Okay, thank you everybody for showing up. This is the last but not least seminar of the California State University first annual virtual seminar series, and I'm so glad that I made the effort to put this together, and I really appreciate all our speakers for coming through to do this, and I feel like we're going to do this again. We had a whole bunch of people who couldn't do it this time for whatever reason, and I know some of the people who are here are going to have more data to share, but I think we should do this all the time. So I think next fall you'll see us again. So let me introduce my last but not least speaker, Dr. Jeet Sukumaran. Jeet got his bachelor's in Ecology and Evolutionary Biology, affectionately known as EEB, at the UT Austin, and that's the University of Texas. Master's in Zoology at the University of Malaya in Malaysia, and a PhD in EEB at the University of Kansas. Jeet also did postdocs at Duke University, University of Kansas, and the University of Michigan when we were lucky enough to have him join us as a professor. He's published in lots of top journals. I just have a list here. PNAS, PLOS, Computational Biology, Trends in Ecology Evolution, Microbiome Evolution, and Systematic Biology. That journal actually scares me when I open it. And I'm going to say he's had 7, now going, I know 8 because we're on one together, 8 papers in 2023, which is just incredible. Lots of NSF funding, and I'm going to say specifically helpful and incredibly helpful in my lab. I've loved having Jeet here. He's on 2 of our papers, and he's been really helpful to my students. We got a couple of papers published that just wouldn't have been possible without his support, and he's helping another one of my students. And I want to just shout out to DendroPy, which is a publication that started in 2010, which doesn't get enough credit. A lot of software doesn't get enough credit, but it's been cited 1,600 times. And it's one of the most amazingly clean packages and easy to read and reproducible packages that I've yet seen in Python. And I really appreciate it. But I want to say, like, this is the core of bioinformatics and why it can be so beautiful, is that unlike other papers where they cite you 1,600 times, that usually means the 1,600 papers have actually used the software. It's not just like, oh, they got an idea from it or whatever, but a huge portion of those people, maybe not all 1,600, but let's say half of them, actually use the software to do science. And that is one, if you write a really good piece of code in bioinformatics, and I've been fortunate enough to be on a couple of these, you're accelerating science across all of bioinformatics and of fields that you've never thought of before. And to maintain this thing all this time for 13 years like that, Jeet, is just, it's an undervalued, what do you think? It's something you've given without compensation, without recognition. So I'm recognizing it right now. Maintaining software unpaid for that long, you should get a medal. I don't know what the medal would be, but you should get it. So that's my thing. But that's to everyone out here. You write some good software, you're helping the universe. So without further ado, I've set you up really good here, Jeet.
No, thank you, Scott. Very kind. And I can tell you what the medal would be. It'll be called tenure. And in seriously, we probably need to think about, as bioinformaticians in academia, there is no structure to give us credit for the type of work we do. It's different types of citations. It's a different form of contributions, and traditional academia in terms of citations and grant funding just does not capture this. And funding agencies the NSF has got a line for maintenance, but I think we have to, maybe in the CSU system, at least, we can start thinking about restructuring the system to foster more practical, industry-focused efforts in credit. But and thank you, Scott, for putting this together. I think it's been great, and it's a great network. It starts the sort of core discussions between groups, and it allows us to have a place to share some ideas with more people we're more comfortable with, and which is why I decided to give this talk a little bit of a different spin. When you first asked me to give this talk, Scott, I was excited to share some results with all of you on some research work I've been doing. It's going to be a research talk. I'd come up with an implementation for species limitation distances that I incorporated some information theory, and this was really filling in a gap in some of the other projects I was working on, macroevolution and speech limitation approaches. But then, as I was working on, the paper was written and incidentally got rejected for being too niche. So I'm still going to shop it around elsewhere. But as I was working and getting that software up to mark, just something I could be proud of to put out there. And that's, to me, an important part of my perspective on software development. I'm not doing this just for a line in my CV. I enjoy crafting software, and it is a craft. It is a craft like carpentry or cooking or basket weaving or painting. There's a zen to it. I enjoy coding, and I enjoy coding well. And I am proud of the work I put out. And just like a carpenter doesn't just put out a table that works, but puts out a table, and they're proud of the table. They want to see the table used. They want a beautiful table. I see my software in the same way. So as I was getting my software up to that standard where it's something I could be happy with, and it's not just, it's an ADHD OCD sort of thing. I need to do it. I can't let it go when it hasn't reached this point. I realized that in the sort of 10, 15 years since I started, more than that, almost 2 decades now I've been working in Python, the landscapes changed a lot, and dramatically. And the language itself has changed. I started with Python 2.0 in the late stages of Python 3 now, and there's some really nice features like f-strings and things like that have just changed the way we think about code. And all fuddy-duddies like me probably are still using old unoptimized methods. But beyond the language itself, the ecosystem had changed. And moreover, I realized that in many bioinformatics programs, especially in many of our histories, like I came up through the ranks through non-formal training, and I think many of us are in the same place. We come from biology or some other places, and bioinformatics until really recently was a nexus field. So some of us may have good biology background, but informal programming and vice versa. So for those of us who haven't had a chance to work in software industry or have formal software engineering type training, we may not really be familiar at all with these methods. We'd have just sort of learned R and Python or whatever we needed to get along on a day-to-day basis, and put off actually formally learning everything, and we're still there, right? So I thought I'd put together this talk, things I learned, things I found useful. Some of these tools have evolved since I've started using them. Some of them changed radically. Some have not, but I note a lot of people, colleagues as well as students, don't use them. So, this is part of a online book or course or something. I haven't thought about what the exact product's going to be. Something for the busy bioinformaticians, a collection of guidebooks, quick recipes you can go to when you want to actually develop software, but you're not actually a software engineer. So this is hoping it's a bit more informal lessons learned, and I think there's going to be something there for both beginners as well as veterans. I think people familiar with the field are going to react, hopefully, with argument and anger, because I'm hoping to see where some of these things are quite opinionated, and it'd be interesting to see where other people disagree. Okay, so let me share my screen. Can you guys see my screen now? Okay. So, I'll start with, this is just, this is about 1/3 of the ground I wanted to cover. You can see two huge things that I'm missing are testing and documentation. I've also got some front end stuff I stuffed in because I thought it was really useful, but I could give an entire 2-week, 3-week talk on testing, and another 2 or 3 week talk on documentation, both of which I think are so missing in academic software as part of our culture. But I'll begin with something that I think most people coming into the field are very concerned about and agonize about, in terms of how they should invest their time, what they should learn, what they should do. And I feel like in many ways it's the least important. It is something that has to be decided because it's the first step, is the least important. Like, what is that what programming language should I learn if you're first getting in the industry? And I'm going to tell you my personal opinion, it doesn't really matter. It absolutely does not matter in the long run. I think that now, if you really want to know what you should learn, just tell me what I should learn. Again, it doesn't matter, but Python or R. And if you really want to know what you should learn first, I think it should be both. But again, it doesn't matter, Python or R. And you will end up using both eventually. There's no doubt about that. And really, the deciding which you want to learn first is like, asking whether you should take your sip of coffee before you begin your breakfast, or vice versa first. You'll end up doing both eventually. And after you get through the basics, I think before you move anywhere else, every bioinformatician owes it to themselves to learn regular expression. And this is the most useful language that most people never heard, let alone learn. It is something that I could not live without. I don't use it just in coding. I use it while actually developing code. I use it to search and replace text. I use it to update entire code bases with a wave of the hand. I use it to refactor code. I use it to manipulate data. It is a way of, it's a system of specifying text patterns, how to extract things from those text patterns, and how to change certain patterns based on other patterns. It's all about manipulating text. And it's a very, very compact, very sophisticated, very precise, extremely arcane way of doing it. But once you learn to speak regular expressions, you will find you have entered this new world, new universe of problem solving. You have tools at your disposal, conceptual tools that you just do not have in any other way. And after that, it doesn't matter. And I think most of us who have got past the second language tier, once you've got one or two languages under your belt, even if you haven't really got them down, more or less you have them down, you realize, you know what, you can pick up any language. And the truth is, by the time you hit your third or fourth language, it's not even a question. I mean, TypeScript, JavaScript, Julia. If you have to, you can pick it up over the weekend. In fact, what happens probably by that time, your coding time is so much in demand that you don't have a weekend to pick it up. But the fact is you can. So to me, one of the least worrisome things, the least important things to agonize over is what language to learn when it comes to bioinformatics. It doesn't matter in the long run. Start with Python or R, add regular expressions for secret superpowers that give you the sort of a Swiss Army knife to surgically manipulate data regardless of the language for the rest of your life. Now, having said that, here's what I cannot let it go without just telling you what I really think about languages. So I know about, I don't know, I think last time I counted up to 24, almost 20. I don't know. I lost count of the number of programming language I've used. I mean, like I said, right now, if I have a problem, it's often easier for me to get into, even if I don't know the language, just figure out, oh, that's how TypeScript works. All right, I'm going to get my text editor colors just right. That's the problem, my own yak shaving problem. Anyway, point being, over the years, where I am now, I find that regular expressions, Python, JavaScript, R, and C++ are the most useful things. This, of course, will vary from person to person, depending what type of work you do. And to be honest, I haven't touched C++ in about a decade. And to me now, it's just a placeholder for a high-performance language. When I really, really need the performance, it's good to have that language in my pocket to be able to pull it out. There are other languages that give you that performance, but this is just a generic language available anywhere. And there's so much bioinformatics code out there that's still in C++. It's useful to know to think around. Of these, I love JavaScript, all these things. That's probably the least useful language of bioinformatics. But I've started using JavaScript a lot because a lot of my development environment relies on JavaScript. I use Obsidian for my thought and writing and notes. And a lot of my IDEs and these sort of Chrome-based or Atom-based applications, and to customize them or to add plugins to use JavaScript. And I'm a pathological tinkerer. Maybe it's the ADHD or something. I always like tinkering with my ecosystem. So whether it's Vim or NeoVim, if you look at my GitHub history, I've got my biggest contributions, both in terms of lines and time, are not to bioinformatics or evolutionary biology software, but to Vim ecosystem, so to NeoVim after that. So anyway, JavaScript is so useful for ecosystem management, and I've come to love it. It's such a beautiful language in its expressivity and its utility, its compactness. Something I highly recommend people look at. And as I shall come back to at the end of the slide, it actually is not just this sort of frivolous language. And the languages I hate the most, I hate R. I can't stand it. I think it's an obscene language. It's a great framework for just quick and dirty manipulation, but I cannot stand the fact so many of his idioms, and I hate the fact that many biologists come up the ranks learning nothing but R, and therefore we have this huge space of packages in R that are really not doing well. There's some bad code out there, and it's not even always the programmer's fault. R is a bad ecosystem to develop complex code in. Java, I use it a lot. It's now a murdered language thanks to Oracle. Oracle bought it and completely strangled. I would not start a new project now in Java if my life depended on it. There's a lot of legacy code out there. It teaches good programming practices. There are other programming languages. I know for some weird reason, many data science programs still teach students C and computer science, and I just think that's archaic. C will be with us forever, but I just do not think it's an important language for data science or computer science students to learn today. Maybe not computer science, data science anyway. In the future, it's hard to say. Julia is shaping up to be a big quantitative academic research language for any sort of math-based thinking or processing. Rust is becoming a go-to systems language, something that will replace both fundamental operating systems development. I think like Pop! OS is coming out with their new operating system in Rust, as well as possibly just pipelining as a pipelining language. I don't know anything about it, but I do know it's very popular. I believe the future front end will lie in two places. The command line, where a lot of development will happen, will continue to be there forever and ever. And the other way front end, and this is in terms of users and non-programmers, is I believe it's going to be JavaScript, TypeScript, CSS, and HTML. The sort of browser-based front ends, even if you're running things on your desktop or your mobile device, browsers are targeting all of them, and they will provide the common front end to interact with the user, and then we package whatever we need in the back end through that. So I think it's a nice separation of responsibility. And even if you don't plan to ever do front-end work, you're just going to concentrate on the analyses and stuff like that. It's a useful language to know, because you know what? That front-end part is important to your code. And this is something we've neglected in academia, especially for a long time, alongside documentation and testing. Okay, or maybe, in 5 years' time, it'll all be prompt engineering. We'll just say, ChatGPT, write code to do this. I work with ChatGPT a lot, and I can tell you, I think the bubble is going to burst. It's not quite going to deliver what it's going to deliver, and it's writing on a lot, and just the provenance of ideas that are coming into it and coming out to it is so murky that I think it's not going to be a sustainable system, either in terms of IP, in terms of where the ideas go and how they get used, and in terms of error checking. But anyway, so I think the future is still going to have room for human programmers, if nothing to train the AI. And I think Julia and Rust and C++, regular expressions, and Python will get you there. Okay. So I'm going to go through some of these sections. If, when I hope to teach the full course or whatever, obviously it'll be much more in depth. I'm going to truncate them here because I think most of us are probably either familiar with it, or there's a lot of resources out there. It's already part of the sort of the general zeitgeist. So, I'm not going to dive into it. Source code management. Let's begin with version control. It's 2023, folks. I hope I don't have to convince you that you need to use source code management. It's fine if you don't, but at least I think all of us should be aware now that this is just the way to do things, right? I mean, it's sort of like using antiseptics in hospitals or washing your hands before surgery. It's not just it's just not a cosmetic detail. It's a fundamental importance to professional workflow to use for some sort of version control in all your code. It's as critical if you're doing hobby code in your basement or in your office to your one-person software team to your collaborative. It becomes exponentially more important when you're doing collaborative code. But I think beyond just good workflow, we have an ethical responsibility to our community of both as community of bioinformaticians as well as the broader community of scientists who use our software to use version control. So we can communicate very well to our users what software they have used and what how that tracks with the code on our end. As bugs come up, bugs get fixed, new features get added or removed, changes in algorithm and logic happens. That version control is critical to linking what you are doing to what your code is doing, to what your users are doing, to what they're finding out, to what they're publishing, and how that impacts human health and behavior and science, right? So if you are not using version control in your own development now for any code you plan to publish, I believe it is at this point in time in 2023 actually unethical or immoral even for the impact your code will have. You owe it to yourself to learn to use it and use it all the time. Backups is a more of a personal thing, right? And one might argue with version control, well, that's a sort of backup, but version control is not backup, even though it ends up by secondarily providing backup, especially if you version control to the cloud. And partly it's because our de facto industry standard version control system we have today, Git, really has a few classes of files. It doesn't handle very well large files. It's bad for that. It really is dedicated to tracking changes as opposed to putting big files, data sets into repositories. And so our larger ecosystem in which we work in beyond the project has, our emails, which are so important for us, the various manuscripts we write, our data, it could be in the terabyte range. So all of these need to be backed up with dates and curated and managed. And backups mean so many different things to so many different people. Everything from, copying to a flash drive whenever you remember to do it, to having a cloud share base. So I'm not going to go, I don't have time to go into detail. I actually have a series of blog posts talking about backup. And the key things here is, if you're talking amateur stock backup, professional stock restoration, most of us growing up with backups think, well, just copying it, putting a hard drive, and that's done. Yeah, that's how we do it until we've had our first failure. And then when you realize you actually need to get that information back, you realize why we think about restoration. So what does restoration mean? Does it mean bringing back your whole hard drive? And from when? And so right now we have a lot of tools that do full system backups, and they work in different ways. It's worth investigating them. I use Restic, which is a software that runs across many different platforms. And I use Restic to roll my own backup system that backs up to the cloud. I love this system because it's deduplicated. So it sort of takes snapshots of every new backup to see what the difference is and saves the snapshot. So almost like Git, except the snapshots themselves are deduplicated one more time. And so it's really, really efficient in the back end. Your first 160 or 200 terabyte upload may take up 200 terabytes with compression, but you can have a very huge new set of data come in, another 200 terabytes, and that might just add like 10 megabytes to that your backend. So it's a very efficient way for your backend to grow, your backup backend. And you can buy just empty space, buckets of space online to do it. And when amateur stock backup, professional stock restoration, it's not just about, does your backup provider give you a hard drive, when you want it. One thing with Restic is you can actually remotely mount a backup snapshot using SSH on your local hard drive. So sometimes I've lost something for whatever reason, I can just mount that snapshot from whatever date, SSH to the directory, get the file I want, and come back. And obviously I've got my projects under version control, but this is the bigger thing, like maybe an email attachment I deleted or whatever. So have a look at that. Have a look at the backup systems. There's cloud-based services now. I can't remember the name of the popular one, like Mozy or something like that. Mosquito, I don't know. Crash Plan is another good one. These are absolutely worth paying for. I like Crash Plan, and especially for your family and more personal things, but your lab wide, you can get these sort of group discounts. And these just run in the background, providing the snapshots of your whole laptop or your desktop environment, separate from backup data for backing up data for a project, and separate from version control and backing up your actual project code. Are there any questions about any of this? Okay, code formatting. I just want to throw this in here. There used to be a time, and in many other spaces, it's still there. There's huge fights about how code should be formatted. I mean, Python has some rules about what the language allows, and within that, there's some flexibility. And from a really early day, programs realized that you want coding conventions. You want a certain way to spell your variable names. You want a certain style to use your variables. Pascal case, spelling should either be all capital, should use underscore separate words. You want a way to name your variables. All your functions, maybe they should be verbs. Maybe things that write to files should be called write, but things that read files should be called pass if they structure it into a data model, but read if they just get binary information. And this is simply because you want to reduce the cognitive task load while you're coding. So much of these best practices I'm talking about have one or two or both objectives: reducing chances of error. Well, three: reducing chances of error, reducing cognitive task load, and the whole ethics and replicability business in science. So, when you coding conventions help that. They help that if you're collaborating other people's code. When you're in the middle of this code base and suddenly you need to do a loop to call a function and write to a file, and you don't want to look back, is it write to file? Is it write file? Is it as string or to string? Coding conventions help you remember that. And they reduce weird errors, like, especially in duck type non-compile language like Python. If the variable to set a spacing is called capital S space, and you assign a number to lower letter S space, obviously in Python they're two different variables, but Python's not going to complain. So you think you've updated state in your object over here, but you've updated an attribute that's not really the correct attribute. And these errors are very, very difficult to find because it's not actually a program error, right? It's the language supports it fine. There are all these add-on tools, IDEs offered to help that. A lot of that is making up for some of the advantages of Python. But one place we can clamp down these things are in keeping coding conventions. So almost from the dawn of time, software engineering groups have always had coding conventions. Even if you're a one-person shop, you have a certain style for your code. You develop it, you stick to it. It doesn't matter what it is. Everyone agrees to that, but what people rarely agree on are coding conventions, what you should do, how we should arrange that. And that's because people have personal preferences. Sometimes it's just historical stochasticity, sometimes it's aesthetics. All of this has been made obsolete with the advent of Black. Black is a software package that's become almost industry standard now for formatting code. Many software shops now just integrate it into their part of their continuous integration. That means whenever you push code commit up to a repository, it gets blacked up and then put it through test before it gets integrated, or it gets rejected if you haven't formatted it according to Black. And so this many IDEs have you can just bring in this Black plugin that runs in the background to format your code, and it really helps. I mean, it's not quite the style I would have chosen, I used before, but the fact is, as I'm typing code, I don't have to worry how I arrange my arguments. Should they be all in a neat row? Should they be indented twice? I just type it, run Black, and it sorts itself out. So next we get to sort of beyond the language itself, and this is getting into more into the core area of my talk. I really, to be honest, the core area of my talk is the whole project management bit, which is I hope I have time to cover at this break. So license and licensing. So this is one of those things that we all have a vague notion of we need to do, or why we do it, and we go out, look on the internet. We often see what the software other software do and uses, and we copy and paste and put it in, and we've heard of GPLs and MITs, and we don't think too much about it. At least that's how it is. But it is an important thing to do. And fundamentally, it's important because it protects you. When you license the code, it's the reason people talk about, release with a warranty and all that is in this country of lawsuits, you don't want to be sued because someone used your code to, maybe you wrote a code to generate a phylogenetic tree, and then they used it to come up with different flavors of beer, and they hated the beer and they sued you for it or something. Or obviously it could be a lot worse, they could have drones crashing into people, or healthcare risks or something like that. And so this just protects you. It protects people whose code you have used, because they have many of them have their own license restrictions they've chosen carefully for their own motivations, and you're using their code, and you have a moral obligation to respect their wishes, as well as legal, and paying attention that licensing makes a difference. And then on top of that, as Scott says, you can think of code as music, and we are musicians. We want our code to be used. So the licensing terms explains and provides ways, tells the public and the broader community how our code can be used. Academic publishing culture leans towards open source licenses. And in fact, open source in some way, shape, or form is mandated in many academic contexts by journal, funding, institutional contracts, all the types of policy. So, we think most of us default to open source. But bear in mind, that's just one small corner of the licensing landscape in the bioinformatics world, right? Bioinformatics is hugely commercial, and there's a lot of commercial licenses out there. And I have no idea what the numbers are, but definitely in terms of money, but also in terms of people, and maybe even beneficial impact of society. It could be argued that industry, commercial bioinformatics is contributing as much, or if not more, as open source code. So we need to think about our licenses, and do we want our software to be used in commercial sectors? Because many open source, by the way, open source license, there are technical definitions of what open source licenses are. In this talk, I'm not going to go into all the license types. Simple Google searches give tons of results. But there are open source licenses that cannot be used in a commercial context. I think some of us are familiar with that, like GPLs and copylefts and so on. So choosing a license is an important part of that. And like I said, I'm not going to go too much in detail about that. I know I picked GPL when I first started, the copyleft thing, because the GPL license expects anyone who uses a code to release their code under GPL. So it's actually quite a restrictive license. And it's not too popular in many sectors because of that restriction. It puts restrictions on how other people can deploy the license. Commercial products can't use it. Many other open source license software cannot use GPL coded software because they want their software to be used in certain contexts, like real free software. But beyond that, and then for Dendropi, I switched it to, I think, MIT, or one of the more relaxed licenses. Because of that, I switched it out of GPL. But beyond the license, I think it's important that we need to understand who owns the IP of the software we create. And this distinction is something I did not know until literally 3 days ago. I was putting in a grant application, and the funding agency required us to open source our licenses, to open source our software. So I thought, oh yeah, no big deal. But turns out within the CSU system, there are some roadblocks to that. There's some people in the CSU system who do not like that idea at all, and want us to come up with a different contract that retains some, pulls back some of the licensing terms of the open source license. So I actually looked up what the deal was, and it turns out it's a bit more complex for us. Institution policy, we are under an institutional policy on that IP. So, I don't know if you know this, under general international copyright law, if you sit at home and type in some text onto your computer, or write it down on a piece of paper, no matter what it is, you are protected by copyright. You don't have to write the word copyright, blah, 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 whatever. You have created this work. By default, you own the copyright on it. And that work is completely within bounds. As long as that work can be copyrighted, there's certain things that cannot be copyrighted, like data cannot be copyrighted, I think, or some forms of data. The Berne Convention protects you. So I'm a photographer. I understood those terms. So going through academia, long before I became a student, I understood that. as I published works. I assume there's the same thing with software I produced as a student and then as a faculty. You know, it's my work, I produced it, I can add whatever license you need. But turns out that in many institutions, you are not the IP owner of your own work. Paradoxically, you get to choose the licensing terms that work is released under, but you don't get to own it. And you get to choose the license, you get to publish it, you get to give the license to whoever you want, but technically the IP belongs to the institution and they're the ones granting the license. It's a weird system. So I looked up, does anyone know what CSU's policy is? Yeah, isn't that crazy? I mean, we've all been working, I've been publishing software in this system for a while, and we have no idea what exactly we're doing, isn't it? It's crazy. So I looked it up. I don't know if this is correct. And obviously, there's a ton of legalese. I found this Article 39 online. And from what I understand, according to the CSU policy, we can use anything we produce as long as it's been produced without extraordinary university support. And I have no idea what the term means. So if anyone can tell me what that term means, that'd be great. Extraordinary university support. We can use whatever we produce for whatever we want if no one has complained about it before. So there's a lot of weasel room there. But basically, you can be fully funded by the school, being paid out of grants and all that. Create some software or a painting on your computer, and you can give it to museums, give it away, license it or whatever, as long as no one has complained about it before, and as long as no one will complain about it, is my understanding of that line. But in terms of what we're talking about today, the next three lines are the critical one. It means that my understanding is we have the ability, unless we have written another agreement, we have the ability to grant licenses to anyone we want and any type of license we want as individuals in the CSU system. And the university does not have that privilege. I'm not clear what the IP is right now of that, but as we have the right to choose who we grant licenses to our software to, and we have the right to decide what form the license is to. Unless there's a prior agreement or our materials have been created with this extraordinary university support. And I have no idea what that means. So anyway, there it is. Basically, a little bit more enlightenment, I think, to where we stand, but I don't know if that helps a lot. Okay, moving on to virtual environments. Now, this is something that I think, people who use it don't even question why we use it. And people who don't use it don't even question why they don't use it. But just like, when I mentioned that analogy of like antiseptic, you wash your hands before your surgery, using virtual environments should be part of your standard workflow for any Python development. What are virtual environments? So you can think of virtual environments like these separate self-contained Python ecosystems on your computer, each with your own set of libraries and dependencies. That by mechanism, it basically links to a specific Python executable. So when you execute a Python program, implicitly or explicitly, when you say Python myscript.py, you're explicitly invoking the Python program. And otherwise, when you just have a script and you invoke it, there's that line in front, user bin env Python. That's the operating system going around finding the default Python, invoking it. So one way or another, a particular Python binary is invoked to invoke a Python program to start a Python code or application. And that is your virtual machine linked to this Python executable. It knows where, based on when it was compiled, where it was compiled and how it was compiled. It links to all the correct libraries, the manuals, the text, everything else follows from this one executable. So you can think of a Python environment as this self-contained, siloed universe coming to life based on where this one Python executable lives. And so over here, for example, I have essentially showing 4 different Python machines. They all live on my laptop. They might share some libraries from my laptop, depending on how I've set up the isolation between these environments. They may share my laptop code. Some of them may run using operating system resources, some may not. But any library I install into this Python will be completely isolated and separated and not available to something on this Python, and vice versa. And in some cases, that's just Python libraries and Python tools. And in other cases, it might be a much more broader ecosystem of tools. So why do we use this? This is system isolation. It all comes down to system isolation. Like if you think of sex coming down to recombination, that's why we have it. The reason we do use virtual environments is to system isolation. These allow you to keep project-specific Python libraries separate from each other, preventing conflicts, right? So if you're working on some analyses that needs this particular tool or this particular library, and that has this set of dependencies, but you also need to run this program that has conflicting dependencies, keep them in separate environments. And you can have both tools running with exactly what they want without interfering with each other. And then sometimes maybe you have scripts that depend on a particular version of a tool, and the latest version on PyPy or some other versions have come out. Again, create a separate environment, cater to that particular tool, its needs, its wants. When you need that tool, invoke that environment, run that tool on your data. And when you're developing, and this to me is the most critical thing, you want your Python is now part of your operating system. There was believe it or not, when I first started Linux, Python had to be installed. It wasn't used in the operating system. It was just one of those add-on weird languages like Ruby, you know. But now Python is an integral part of an operating system. Your operating system uses Python and use a particular version of Python. Its critical libraries and resources are all compiled against that version of Python. And so if you come along and you have a library you want to install that might have a different version of a micro version of a Python, or made conflict with the operating system libraries that it requires, you are out of luck. And so creating a development environment virtual machine allows you to create a development environment tailored specifically to your needs. It allows you to mess with the environment. It allows you for crash. It allows things to just try out new libraries. It allows you to replicate. This is such an important one. It allows you to replicate a clean slate on a user's computer to see how your packages install and uninstall, for example. There's just so many different ways and reasons you want to have a Python environment that help development. But the biggest one is this isolation of libraries, and in terms of development, isolation of your development environment from the broader operating system, both for the safety of your operating system, for the integrity and robustness of your code, and as well as because so you want to be able to select and fine-tune the ecosystem your development goes into, or the code you're developing against relies on the libraries and so on. So, which ones to use? And again, I can, I actually originally this whole lecture was a 2-hour lecture. So I'm going to cut it down to one slide. Something that ships with Python, VM, it's there. Annoyingly, if you have a Linux distribution, it doesn't ship with a default Python that comes with Linux, Ubuntu. For some reason, they strip it out. You have to add it as a package. But most Python packages that you install come with VM built in. It's a very lightweight one. It does the job, and it doesn't require any other things for you to install, which is unless you are in this weird Ubuntu scenario. And I think something most people can start off with. It's not got some great meta management. It just creates the virtual environment in the directory you ask it to create in, and then every time you invoke the environment, you have to go to that directory or essentially find your own path to that Python to invoke it. There are some tools you can add on top of it, like virtual environment wrapper, that provide a management context. But that's about it. So something that is more specific for tool usage is pipx, and I think this is wonderful. If you are not a developer, if you are a bioinformatics user, or even if you're a developer but there are just some tools you want to use, pipx will give you what you want without any muss or fuss. You don't have to worry about creating environments. You don't have to worry destroying environments. You don't have to worry about anything. Pipx will, I'll tell you how it works in the next slide. And then if you're a developer, if you're developing packages, there are others, but you want something like Conda. And the big thing Conda provides is the ability to have different versions of Python and create virtual environments with different versions of Python that are not just your operating system Python. VNV and pipx both are thin layers on top of the existing operating system Python. They protect your operating system Python, or whatever base Python you're using. You could maybe install your own Python package and then run VN on top of it, but they're not really rich self-contained ecosystems in the way Conda is, which comes in and brings down an entire universe, almost a mini operating system within our operating system on it. within itself. Not quite, because there are Docker containers that do actually that, but Conda is the next heavy thing. So as I said, BNT is built-in, lightweight. It sits on top of existing Python. It's virtual environment wrapper, gives you command line completion. It's a good environment way to do things if you're just working on hobby projects. And don't get me wrong, I know many pro developers have just gone back and used virtual environment, and it's just something they're used to. And it doesn't have all the heavy boilerplate of these other installations, and sometimes they use it in context, in conjunction with the other tools. They just want to do some quick and dirty creation. I have used this. I can't remember how to use it very well. I've just been using Conda for so long, but it works, and it's something everyone should think about if you don't want to get too much into it. However, I think for most other people who are not developers, PipX is probably the way to go now. This brings something beautiful that JavaScript has had for a long time. I think this is magical. I just discovered this a month ago. With PipX, I can go to any Python package on GitHub and run it on my computer without any installation, explicit installation on my part. This command, I can go to a brand new computer that has PipX installed, and I can run some trees on that without doing any Python pip install or anything. And I can do this for any tool on GitHub, which I think is just amazing, absolutely amazing. So right now, if you write a piece of software and you want people to use it, and you have some really complex stuff that they have to download and install and get everything running, as long as you set up your project well, so Pip knows how to do that. And I will tell you how to do that in the next, well, it's going to be the next 20 minutes, but I guess 5 minutes to finish it off. As long as you can do that, your users can run your code directly off your remote cloud repository with just this one command line deep in their pipeline script. And so I think that's amazing. And I think this should be something we should all aspire to do with our software, just for usability and accessibility concerns. I'll tell you how you want to go about packaging your tools to let users do this in the next few slides. I just want to mention Conda. And so Conda is just the most biggest and heavyweight feature thing I'm talking about here. Really, the big advantage is it lets you run different versions of Python, and it brings in a lot of other stuff. It lets you manage R and Jupyter notebooks and things like that. And I find it really heavyweight. Its interface, it's got such weird idioms to me. The way you look up environments are different from the way you kill environments or delete environments, different, you rename them. I don't know, but I just haven't found I've actually found alternatives to move to, but it's just inertia. So anyway, to basically pick a virtual environment system and use it always. What matters is you integrate virtual environment management into both your development as well as your usage analysis workflow. What doesn't matter is what virtual environment you use, as long as they minimally fit your needs and you're minimally comfortable enough to use them. And so, based on this, pick something that fits your needs. I would say for developers, Conda or mini Conda, but everyone should make their packages run under PipX, and for users, PipX is the one you should be looking at. Now, one question I have for everyone, and I have my own answers, why not throw everything to Docker? For those of you who don't know, Docker is a container app. And so it's like the self-contained operating system. You pack it with everything you need, including your scripts, and then you give it to people. And they will run it, and it sort of reboots a mini computer inside their system with everything they need to run your program and even data. So it's like, it really is like shipping a mini container of a computer. So why don't we all use the Docker? I'm not going to tell you the answer now. Okay, packaging. Packaging is the of getting your code base into a shape that allows it to be distributed by the Python ecosystem, which includes pip and so on. Pip is an installer. It's not a packager, but it relies on you packaging a code so it can be installed by end users. I believe we have if we are writing software out there beyond just padding our CV to keep our job, but to actually serve the community, we need to think about packaging just as much as documentation and testing, because that's how we get our code to the user. What is the state of Python's packaging system? The less said, the better. It's a mess. And if I could swear, I would swear now. It is just a nightmare. Competing, overlapping standards have come up and dropped side, and some things overlap, some things don't. It's really frustrating, especially when you look at ecosystems like R and Perl that just have it so down. Setting up a workshop in R is so easy to do. Even pre-Docker, and setting up something in Python used to be a nightmare. Pip has revolutionized things so much that it's from the user side of things is much better, but it's a nightmare still on the packaging side of things, and it's a mess. But it's going to get better, and that's why I'm not going to talk about packaging, which is setup tools and so on. There's a ton of stuff out there. I'm going to talk, and this is what I really hope to be in the last 5 minutes, the main focus of my talk, project management under Python. In about 2021, a final standard was that PEP 621 was accepted as finals. And this had proposed essentially this file that's going to be part of your Python project, PyProject TOML. TOML is a markup language like YAML or JSON. And this is the way of the future. And if we are writing Python projects today, creating Python projects, we need to think about creating a PyProject TOML file, just like a README, and that gets accompanied with every project. This is how Python in the future packages are good. The entire life cycle of the project, from development to environment to dependency management to package management to deployment, is going to be sorted out through PyProject TOML. Before, like, we have all these files. These files are artifacts of all these different systems for Python packaging I talked about, from setup tools to distutils and so on. And they get these different files get read by different tools at different phases and for different things. If you're packaging something as an archive, you have to put the files that go into archives into the archives over here. If you're packaging something for end user distribution through PyPy, these files go over here. If you're packaging something as a zip archive for source code distribution, you have to mention things over here. And then some things get mentioned, shared by all the files. And then, of course, a huge problem I face is beyond the code itself. Things, what are example files, data files, resource files, configuration files? How do you put them? How do you package them? How do you let your code find critical JSON or supporting files once it's been installed on a user system, when it could have been installed through setup tools, maybe the user downloaded your zip archive and unpacked it somewhere, is running the code over there, or maybe your user is running pipx. And in all cases, your code has some important things bundling with it that is not Python code, that you can't actually put down in setup Py. How do you make sure your package at this end user where it's running has access to that data? It is a nightmare. It could be done before. We have all done it. Well, those of us have done it have found ways to do it. But it's much, much easier now with this PyProject TOML. There's so a lot of information out there. And the thing is that creating the PyProject TOML is just part of it. And here's the sad news, folks. Today, you're going to spend, even if you say, oh, I'm so excited about PyProject TOML, I'm going to figure out how to do it, I'm going to create my file. You're going to create it, and you're going to find, you know what? You still probably have to have setup.py, because it's still not completely accepted and used everywhere. So right now, we don't have 25 problems, we have 26 problems. So sorry about that, but hopefully in the future, we are going to sort this out. So with this file, you're able to cleanly specify this metadata. Before you could, there's all a bunch of strings. Now we can do structured metadata. We can talk about dependencies. We can talk about classifiers. We can talk about URLs. Before, our setup.py was used by setup.tools, but to run setup.py, your local ecosystem needed to have setup.tools. So how would you tell your Python ecosystem that it needed to download setup.tools, because that information was inside setup.py? There's a chicken and egg problem. That's been solved with this PyProject TOML. You tell your builder what's your builder you need and what's your what the requirements you need to build this project. And today, we have a whole set of tools to help doing that. Poetry and Hatch are two really trendy ones nowadays. Poetry was an earlier one. Hatch has come up to solve some of the problems Poetry has. They don't really do the same thing. They sort of do the same thing. They all roll in together. package and management, packaging, as well as deployment, as well as things like virtual environments, as well as dependency managers. So they can create virtual environments for you and bring in all the dependencies based on recipes. So they're much more than just Conda or Pipex. They're entire project workflow tools. And finally, I know I'm out of time. Scott, do I have 2 more minutes of grace time before, or do I have to shut down now?
Yeah, I mean, I'll just tell everyone you're welcome to leave. Obviously, you didn't have to be here in the first place, I suppose. But I actually, if it's just a few more minutes, this is a great recording, and I think I could play this for people in the future. So let's finish as much. It don't take too long, but finish the recording, because and if people can stick around, it's great, because you don't get this everywhere. So
okay. Well, yeah, no, I mean, really, I would love to. This can easily be expanded. Each one of these sections, I mean, I spent most of last night removing stuff from this presentation, and like I said, 2 huge sections I didn't manage to cover, which I think are critical: testing and documentation. But this is something I think I want to talk about, especially because I feel like it's another neglected area when it comes to bioinformatics tool development. This is my personal opinion. The future is now. I believe the future of software usage, at least in the near term, before AI takes over and gets integrated into our heads with these patches, that it would be CLI, some sort of command line interfaces. They've always been around. There's a famous essay by one of the visionaries of science fiction. In the beginning, there was the command line, the whole cyberpunk movement. Can't remember his name now. Not William Gibson, his writing partner. But anyway, command lines will be around. They have many advantages. They'll be around forever. Bruce, what is that? Bruce Sterling, is that right?
Bruce Sterling was a.
That's right. Exactly right. But I'm sure you folks have been using tools now that have this sort of Chrome or Atom-based front end. I use Obsidian. I'm obsessed with Obsidian, and they run. Excuse me, sorry. HTML and CSS and TypeScript, they're essentially these sort of Chrome-ish front ends, like or Firefox, so much. They make great, elegant front ends. They're very featureful. They run on any browser. They run on devices. So when you invest your time to create a front end for Chrome, it'll run anywhere under any user, and all the stuff about is the user using a touch screen, is the user using a keyboard, a mouse, where it clicks, the resources, is the user have a tiny smartphone or a desktop. All that is sorted out by that ecosystem. So there's some real benefits that you can just focus on designing your front end. So even if you're not really into GUIs, HTML, CSS, and types can give you a minimal way to communicate, provide a way for your users to communicate with your program in a very structured, clean way. So when I say command line, folks, we are in a different universe today. This is not the command line I grew up with. You can write, there's absolutely no reason you can't write absolutely stunning command line programs to work very, very easily using some of the libraries we have today. So this is rich. And at the risk of running live code, you guys can't see my second screen right now, right?
No.
Okay, let me just invoke it. All right. Sorry, let me see if I can switch. Do you know how I would do that? Switch my
maybe you stop sharing.
Oh, okay, I can stop sharing the screen as well. There. Okay, can you see this?
Yes.
Okay, so this is just my normal shell, right? There's nothing to it, and this is just a demo of that rich code, and you can see it. I mean, all of this is just print statements, different forms of print statements. You can add color, you can add blinking text, you can create tables by inheriting from table objects and populating them. Tables in the shell, really complex tables with borders and colors and so on. You can have syntax highlighting for free. You can just print some code and say, give me some full markers. You can print your markdown text. You can read. You can in one line of Python, you can make your own command line markdown reader with formatting. So it's just absolutely amazing. And then I now have to go back to that other, back to my slides again. Sorry. Let's go back to my slides, which is here. Okay. And that's just taking stuff on your command line and making pretty output to the user. And again, this is not just making things pretty. I do it, I confess, I do it because I love the way it looks. It's part of the crafts person inside me. For me, coding is a craft, and this is very much part of the craft. But beyond the craft, it makes a huge difference. I mean, how many times have you seen that 20-line Python stack trace or LaTeX stack trace? It's 4 o'clock in the morning, and you're just trying to figure out where that error is. Throw in some color. We are primates, right? We respond to color, and throw in some color and you see it right away. And then once you get a little bit of consistent color, it's part of your mind body loop, it's part of your muscle memory. You don't even think, where's the error? The stack trace happens, your hands are already editing the code because it's all gone through beyond you, without you actually consciously processing it. So color, structure, organization of output helps. After I told you I updated my code to having some fancy front ends, it became so much easier to pick up problems when I was running analyses, because little warning signs would flash by in orange, for example, or because I'd separate the output into expected input, output, I'd see more text appearing here as it flew by my screen. In fact, I wonder if I can show you. I hope if I have time, as everyone's leaving, I can run that code. So anyway, it makes a huge difference. It makes a huge difference to your fatigue, to your error, and it's worth investing. And for your use.
Let's end on this point.
Okay, all right, we'll do it. Thank you all.
You can just show us that one thing, and then we can go, or is it?
Okay, no, I think I just want to show you one more thing. Am I sharing my second slides? No. Okay, there's one more Python library that actually lets you create full-fledged widgets in your terminal. This includes spreadsheets and clickable GUIs. So you can actually, through the shell, have an entire GUI application. That's called textual. All right, thank you all. So sorry for going over time, and so sorry for the technical delays getting started. I appreciate you letting me share this information with you, and I'm happy to discuss any of this with you more.
That's fantastic, and I hope if you could share the slides with us, because I know you have more on them. I could put that in the Google Dropbox, any link you have to the slides, or you could just send it to me and I could put them in a Google Drive or something. That would be, I'm sure people would really appreciate that.
Absolutely.
Lots of links in here,
Yep, no worries.
Yeah, great. No, if anyone has any questions, if you still can hang around, that was incredible knowledge dump that I can't, it's just incredible. So I actually have one thing that I would like to do educationally, and I'll have to talk to you about it, because what I really would like to do, I have trouble, I'm way behind, and I think a lot of the professors are way behind. Because we learned to code a while ago, and now I don't even have time to code, and I'm trying to keep up with all the changes. You actually do, to your credit, you're in there. It's like you're still at the bench.
No, Scott, this was catch up, the last 2 weeks in preparation for that. I mean, I was
you're still coding though. I still see you do it, but educationally, I want people to have all this. So what I would love to do with you at some point, if you're game, and I think others might appreciate that, is come up with, and I love simple examples. I like simplest, like kernels that explain everything, right? So for instance, I will have one little algorithm, one explanation that explains all the ways algorithms work, or all the ways this code works. So for instance, let's say I wanted to teach all of these different subjects, like how to update your code, how to do GitHub, how to do version control, how to do text, all of that kind of stuff. It would be great to have a project the students work on, all right, that's small, that you could finish a few functions, something that works, something that's interesting, but it's not enormous, that it's just, as a training exercise. And then you say, okay, we're going to do, put this on GitHub, we're going to do version control, we're going to do the text manipulation, we're going to do black, we're going to do all that, all on this tiny little bit of code. So you don't spend all your time coding, you spend just enough, and then you say, Now, how do you update it to do a version? Now, how do you update it to this? Now, how do you make it a package? Even if it's ridiculous, you would never make a package for such a ridiculously small bit of code. But but who cares, right? Your point is to learn how to do the packaging, not how to do the coding. How do you make, so if I could sit down with you, and we could come up with an educational exercise I could fold into my course, I think it would just be like, that's what was really missing for a lot of students. I so many little details to train them, but frankly, they need it because they're going to go out in the real world and they're going to ask, did you do version control? Did you do, do you know how to make a package? Do you know how to make this? How do you make that? And I feel like we're neglecting their education, except that it's so hard this is why people still teach Java, right? They still teach Java because that's what they learn, and they didn't have time to learn Python.
Well,
it's not that hard, but no time.
but Eve Scott, very good points. But even that whole packaging with Java, I mean, Java only goes part of the way. There's all the other stuff that comes to it. Listen, I would love to help. I actually have not a formal exercise, but I have basically when my students write code, they get it to a point where it works really well, and then the packaging is the next step that comes in. So I've gone through that. I'm going through the exercises now with one of my students, and I would love to help you with that. But maybe we can, both of us can talk about, your Bioinformatics Part 2 or something, where we go through the documentation, the testing requirements, the packaging requirements. This presentation is, in fact, the title I have here is part of a course I'm envisioning. It's not a course I have any idea where it's going to go. It's just something I wanted to create because I kept needing to teach these things again and again. It's called Beautiful Bioinformatics. So if you want to talk about, I would love to talk to you about that, getting some of these lessons into your course and maybe packaging some of these other lessons into their own follow-up course, which we can, and maybe with Arun can teach here at SDSU or something.
Just like everything, once you learn a little bit of coding often, or learn the basics, you can go all these directions. But you got to have that basic, and that's what I'd love to learn. So anyway, I'm sorry, I sort of took a lot of time here, but Jean, did you have questions or anyone else?
No, I agree with all these. I struggle with these like pre-pack, like you want to show them all the things, like we did like a day on Unix in the command line, and but I kept saying like, you just got to practice it. You got to practice it. And I'm like, but I can't really give you a thing to practice on because I don't know. So yes, I think this is something we can do better with. Yeah. I appreciate your thought. There's
different levels. It's undergraduate and graduate.
Yes.
And all stuff, but
yeah,
we all have our little, educational thing. I'm really good at teaching things when I know it. That's a skill I have, and coming up with things that are exercises. But anyway, let's let Trevor ask a question.
Hi everyone. Thank you, Dr. G. That was quite an amazing presentation, and I'm taking Dr. Kelly's class this semester, and I really wish that this was one of our first presentations we had during the start of the seminar series, because this is actually so relevant to my class I'm taking with Dr. Kelly, because we're literally doing Python projects, and I've been editing everything in like my base environment. I have not been paying attention to like any of these best practices, but it's definitely something that can really enrich the bioinformatics course. I think another question I wanted to ask is, if we're working with workflow management software like SnakeMake or Nextflow, how do we really go about handling licensing issues, especially if we want to publish our pipelines or kind of make them available for public use? Because we incorporate multiple tools, some closed, some open source. How might we go about that?
That's a great question, and I know the great question is a platitude thing people say all the time, but I really mean it's a great question, and I say that without shame because I don't know the answer to that. I like I said, the whole copyright thing took me by surprise. The fact that we don't even now I'm unclear who owns the IP to that, and I usually have just ignored it in the sense that if people want to make money of the software, let them make money of the software. I am going to just do everything open source. If I'm using tools that people have licensed in different ways, it's up to them to figure it out. I've got that. I've got it. I don't know. So basically, I didn't care. But the fact you're asking the question shows that's the correct way to think about that. Exactly how is that software being used? And the reason it's important for us to do that now is because all this stuff, this fuzzy area between licensing and not licensing, is making a huge difference in this world of LLMs, because that material is all being sucked into these AI and being used in many, many different ways with no real clear provenance. And so now it's up to us. We need to decide, do we want our material to end up in an AI training the future? I will say this is a difficult decision to make. I'm okay with it. I feel like I have learned more. I think some awful theft and piracy is going on in the AI world. People are being screwed over in so many different ways. But there are gains. I learned TypeScript. I wrote a full TypeScript plugin in a day. And I talked about being able to learn languages over an afternoon, but TypeScript is a bit complicated. And while I might have been able to learn TypeScript in a day, I would not have been able to write error-free TypeScript plugin in a day. And that sort of augmentation and enhancement that AI does, not just replacing humans, but augmenting humans, is going to change the world. And that relies on this material being in the public so that AI can be trained on that. So I'm okay with that. But that is a very personal decision everyone has to make. And that includes a tool chain that gets you to where your software is. And so that's just part of our moral duty now to look into it and see how that works out. But I don't have a yes or no answer. This is how you do it.
No, but that was very insightful. Thank you, Dr. Jeet. Yeah.
I got to call it here, and I'm in charge. So I'm the host, unfortunately. But this is an incredible discussion, and Trevor was talking about this current class as being a place, but it's actually the next class where we do advanced bioinformatics that I think that that's where I would really incorporate this. You have two jobs here. One is just to teach I have to teach what a variable is and what it means. But next semester, that's the time I would love to try and help incorporate some of this in. So I'll talk to you. We'll be in touch.
Yeah, I'll be happy to drop by.
On it. We should write a paper on how to teach this. That would be,
yeah, no.
How do you teach this clearly fundamental stuff in a reasonable, direct way? I think I can help with that because I am dumb, and that's helpful sometimes.
I want to talk to you about that, definitely.
Let's do this, yeah. And I think Arun would be on board, and maybe we can do it as a CSU from all the professors.
Yeah, that's awesome. Yes, if everyone wants to join and brainstorm about, yeah.
Sounds like a sabbatical project for me. I'm on sabbatical next semester, so I'll get on it. All right, thanks a lot again. Thanks everyone for showing up. What a great way to end it. Like thinking about the future. All right, take care.
Bye.